Exciting stuff here, learning great things. All right, so we're going to be moving on to our next presenter before we do get a break in here. So next we've got Ryan May, who joined the Unidata Program Center as a software development staff in January of 2013, before his purgatory ended, but now has since finished up his PhD as well as his bachelor's and master's degree from the University of Oklahoma, Boomer Sooner. He came hoping to work on various things, and Python was one of them, and he's been able to do a little bit more with that. So he's going to add some perspectives from a new package that he's been working on since his days as a graduate student, and with myself there as well. He was one who encouraged me initially to get into Python, so you can blame him for lots of things. All right, welcome, Ryan. Okay. How are we looking up there? Let's see. Okay, and then there we go. Okay, so I'm going to talk about MetPy. This has been something that I and a few colleagues have envisioned since graduate school and kind of just started trying to run with it since I think there's a need. And I'll talk about what the goals are about this. Who am I? As Kevin alluded to, I'm a software engineer at Unidata. I've been here for a year and a half. My primary work is on the Threads data server. I'm a Pythonista. I like long walks on the beach and watching Longhorns lose football games. And there's my Twitter and GitHub handle. So what is MetPy? Oop. There we go. MetPy is a Python toolkit for meteorology, and this is very early development, so it's a toolkit that's currently limited in features, but ambitious in goals. We want to read in weather data formats, we want reusable calculation routines, and we want meteorology plots that sometimes get neglected in the general scientific ecosystem. We want to be anyone to be able to reuse these routines. Educators for producing synoptic weather maps, researchers to be able to reuse routines in research papers as opposed to having to recode their own. And we just want this to become a community resource for hopefully collecting very useful bits and pieces of code that everyone produces to get their itch scratched, but don't know where to kind of put them so that others can make use of them. The design philosophy, we're trying to hit, in general, this GEMPAC-like spot where you can do scripted weather analyses, produce nice publication quality figures, and luckily Matplotlib already does a good job of producing publication quality graphics, just not with the meteorology focus. And fitting in with the rest of the Python ecosystem, be able to fit into with NumPy routines and Matplotlib for plotting or other similar plotting packages, or be able to reuse, pull in your weather data and be able to plug it into SciPy routines like ODE integrators or various things that exist within SciPy. So just hitting this hole where it's the weather-specific things, but it works with all of the other pieces that exist already in Python, because we don't want to be reinventing wheels that exist. The biggest goal is to make it simple to use with your own data. I know personally I've found that to be a problem with GEMPAC. It's great if you have things in gem file format. But like me, if you're a radar guy and you don't make gem files, that makes it a non-starter. And so there was always that when I was in grad school. One of the design trade-offs we made in terms of being simple to use it with your own data is that for using the calculations, we're trying to enforce unit correctness. So this means you do need to attach some unit information to your data. Unlike Stephen's trade-off there, I found in the calculation routines, half of my documentation was just what are the units for each of the parameters going in here. So for potential temperature, you've got to have pressure in millibars, you've got to have temperature in Kelvin, et cetera, and just having those units baked into your data makes all those calculations just work, and you don't have to think about it if you just pay a little bit of upfront cost. And the examples I'll show later, it's not too burdensome to annotate those with units, and you pretty much already need to know what your units are if you're going to get the right answer in the first place. And then the other things we're trying to do is make sure we get this well tested and documented so that this can keep going and that it's not something that bit rots. And then we're also right now, development's very much driven by use cases. So, it's not, we have a goal of, exhaustively doing the GEMPACK grid diagnostic functions. That's a nice goal, but at least with the current resources behind it, that's years away. So right now it's, okay, what weather map do I want? What is the use case here? What holes do I need to fill to get that particular weather map? And just growing it through various examples and applications. Let's see, all right. So what can it do right now? Well, we can read data. And being the radar guy that I am, it can read Nexrad files, level 2 and level 3 data. Pure Python, these are things I've cooked up over time for needs I had. And again, I didn't have a good place to put them, so MetPy became a nice home for anyone working with radar data or NIDS products. There's some useful things, pure Python. So you don't need a lot of burdensome prerequisites to get these working. So for example of NIDS decoding, we have some imports, and we'll cover those a little more. I want to focus on them. So we're reading a bunch of files. I've got a TVS product, so detecting tornadoes. I've got mesocyclones, hail, the reflectivity data, and storm tracks. All of these coming in from NIDS files that you could get from NCDC or across NOAA port. That's great. Okay, so what happens if I look at the TVS file? Okay, I get some information. This is very low level, so I don't expect anyone except someone trying to learn about Nexrad product format to really care about this. What might be interesting, though, is here's the alphanumeric data that's in that TVS product, and you get the nice text representation. This is verbatim what's in the file. I didn't even have to cook up this format. They actually put out line by line the ASCII representation of the product. Okay, we have that. Okay, so if we combine these, and I've got some plotting functions that kind of hide a lot of the details behind it, but just an example of what you can do just in Python. With a few of those plotting functions, here's a combination of various products from the Central Oklahoma Moore storm, the F5 from a couple years ago. And we have the reflectivity field in the background. We have some storm track output from there. We have the TVS, it probably isn't showing up back there, but take my word for it, there's a red triangle there indicating the location of the tornado from the radar data, as well as the square here is representing the hail detection algorithm. So you can just combine all these products, all through MetPy. No other work required other than these plotting functions, which once I clean up and come up with a sane API that works for that, those will go in there eventually, but right now they're very much hacky code. MetPy also has calculations, so we have some basic calculations like heat index or calculating wind components, kinematic calculations like vertical vorticity, thermodynamic calculations like lifted condensation level or just a basic dew point calculation, and some turbulence calculations, which comes partially from my collaborator Sean over there, who's a boundary layer guy, so that's his itch to scratch. So again, a lot of these things that exist in here come from certain things we needed to accomplish things. A lot of the thermodynamic and the basic calculations come from trying to make a skew-T. So that they're very much slanted towards that right now, and hopefully over time from that starting point we can get a few of those holes filled in to expand the scope eventually. Calculations are simple and independent to try and make sure we can reuse these, so that you just throw some NumPy arrays in there with units and you get them out. So if you want to reuse this in some code that you've written and you just need this, you don't want to have to recode a potential temperature function. Well, there it is in MetPy, pull it in, use it, great. So an example, all right, it's 86 Fahrenheit outside here. We'll say that's about right for Boulder today. Station pressure is at 860 millibars and the relative humidity is 40%. So what's the dew point? All right, well, we can import MetPy calc as mcalc. We grab the units registry here from the units module. All right, the temperature, 86 times units in degrees Fahrenheit. Pressure, 860 units millibar. And the humidity is 40 divided by 100, because as we can look at the documentation, we need humidity 0 to 1. Great. All right, there's the dew point. And we can convert it to degrees Fahrenheit, and we get out the nice, it's a 59 degrees Fahrenheit dew point. Great. What's the lifted condensation level look like for that same set of conditions? All right, well, there's the LCL function. We pass it the pressure, the temperature, and the dew point. Bam, 690.7 millibar for the LCL. Oop. All right, given those conditions, what's the parcel profile look like? So this means lifting that parcel profile up to the lifted condensation level, dry adiabatically, and then lifting it moist adiabatically once you hit saturation there. Very common Thermo 101 and meteorology problem. All right, we need NumPy here so we can actually have an array of pressure levels, because I want to see it 860 the surface, and then we'll just give it, the standard levels here. Say that they're in millibars, and then we say Parcel Profile, here's the pressure levels I want. The starting point needs to be the first value. And then we give it the starting temperature and dew point, and there's your Parcel Profile. It starts at 303 Kelvin, 302, 285, etc. So then plotting. Right now, plotting is kind of, there's not much you can't do in Matplotlib. You already have contours, you've got color mapped images, et cetera, et cetera. So the big thing that's lacking there is SKUT. And then there's also support for color tables, because that can be a bit of the obtuse part of the Matplotlib API. It's a lot of power, but if you just want to quick define your own color table, it could be a little bit hard to bite off. So there's some support to try and simplify that. So let's plot some sounding data. I've got some test data built into MetPy in the Git repo, so I'm just going to load a basic sounding out of there using NumPy's text parsing. And I'm going to grab pressure, temperature, dew point, and the direction and speed from just a sounding I think I ripped off of the Wyoming sounding archive. And then we'll calculate the U and V components using the getWind components function from MetPy. Great. So here's the SKUT. Create a new Matplotlib figure, wrap a SKUT around it, and then skew.plot, pressure, temperature, make it red, and plot pressure, dew point, make it green, and then plot the wind barbs. And that's what you get. How many people here previously have tried to make a SKUT in Matplotlib? How painful was that?
More than this.
I've seen many approaches, including some people just actually skewing the data in the plot command, and just always bothered me. Trying to get Matplotlib to skew things was not an easy thing to pick off. So it's nice to have this in a library where everyone else can use it. But this isn't the only thing. Okay, we have the slanted temperature lines and the pressure lines, but if you're doing sounding analysis, what you really want are dry adibats, moist adibats, and mixing ratio lines. So there we go. Now you've got the moist adibats, dry adibats, and if they can't quite see it, there are the mixing ratio lines right there. So easy enough to get all the standard lines on there so you can actually make sense of what the sounding's doing. So besides MetPy, I want to talk real briefly about Siphon, which is, the name comes from trying to suck data down the pipe. So this is the name of our Python API that we're trying to put together for the Threads data server. And the idea being, make it easy to get data. As we saw earlier, Kevin talked about getting data using OpenDAP, which is great, except you have to do a lot of thinking in terms of index space. OpenDAP is, I need indices 0 to 100, maybe skipping every 10, but it requires some knowledge about the data and some thought, and it's easy enough to do, but there are easier ways we can do. How many of you are familiar with Threads at all? Okay, so Threads is a Unidata project that works to sit on top of your data collections and provide a variety of different web services on top of those, and using the Netcdf Java library to abstract away the different types of data behind the Netcdf data model, or actually the common data model, but think Netcdf for a lot of it, especially GRIB collections, so you don't have to worry about GRIB. Let us worry about that so you don't have to. If you haven't worked with GRIB before, it sucks terribly. So you have the Threads data server. It sits on top of the data, and then it provides services on top of that, like OpenDAP, or we have an HTTP server which lets you just download the raw data files. But then we have things like WMS, or what I'll talk a lot about is the Netcdf Subset service. And that allows you to get a subset of your data in Netcdf format. But instead of needing to use index-based queries, you can just query in latitude and longitude or date time, and what we call coordinates, subsetting in coordinate space. So we have a demonstration server here. If we go there, we see you have a catalog here, and you can go in, click, and look at all the things. And one problem, as mentioned before, is searching this can be a little tricky. But if you know what you're looking for, and if the people hosting the server do a good job of laying out the catalog logically, it's not too bad. So you can go down here and okay, here I want the GFS 1 degree forecast. And one of the things in addition to handling GRIB files, is we can provide this latest collection. So automatically we update latest pointer to the latest data set that's on the server. And so you don't have to worry about forming this date time string to try and figure out what the proper URLs is for the data. You just point to latest and get it. Okay, there's the latest, go in there. Well, that's great. There's all this information. You see all these different access URLs. But trying to do that programmatically is kind of ugly. And so if we, really that's the HTML representation. And if you really want to see what ugly looks like, we can look at the XML. And that's not a human readable format, but machines can do it all right, but nobody wants to be dealing with that. Just yuck. So what happened to my presentation? Haha, foiled you. All right, so Siphon is our API for talking to threads, and part of it is just parsing those catalogs for you and making it easy to pull out the information you want there. Go get the data sets. Go look at, just get the access URL you want. For instance, I just want you to go get this data set through NCSS, the Netcdf Subset service. There's also features in there for talking to our radar query service. So being able to ask the thread server, can I get the latest NIDS file, latest NIDS reflectivity product for FTG, the Denver radar? Or give me the last hour's worth of data because I want to loop over them. Providing queries like that. And this provides a nice API from Python to do that rather than generating URLs yourself. So here's an example. We're going to use Siphon to get forecasts from the GFS. And we'll start by finding on threads. I kind of showed you where you'd go walking the catalog. So there I grabbed this URL to best. And so I just import TDS catalog from Siphon. And I say, OK, excuse me. I just want the best data set. There's only one data set in that catalog. We'll pull it out. Great. OK, here's the list of access URLs. So once you've got that data set, you can hit any of these. I mean, so here's the OpenDAP URL. So you could throw that into Netcdf for Python and go do it the usual way. We get Netcdf data remotely. You can also use the, Best doesn't have it. So I was going to say you could use the HTTP to download it, but you can't do that with Best. But if you had this pointing to just a regular file, you could just download the raw file. Okay, so let's get that using NCSS. Okay, we'll pull in this NCSS object, and we're going to point it at that URL. Okay, I'm going to use Python's datetime module to formulate today's date in UTC. And I'm going to set up a query for NCSS. I want the data for this longitude-latitude point, negative 10540, which is basically Boulder. I want the data for the vertical level 100,000 pascals. That's in the native coordinates of what the data set has. You can get that if you looked at the metadata for the data set. And for the time range of that query, I want now, start time now, and then end time now plus 7 days. That's, if you're not as familiar with Python, Python datetime has a datetime object, and it also has a time delta for representing differences in time. So what this is saying is take now and then add 7 days to now. And so I'm asking a request of 7 days data into the future from today. And the variables I just want you to give me temperature isobaric. And I'm going to take it in Netcdf4 format. And the other benefit here is I don't have to download the whole grib file to go and get this information. I just ask the thread server for what I'm wanting. And so this is a much quicker query than downloading a gigabyte grib run from NSEP. And so when we get the data, it's just a Netcdf4 file. So we get it, and we look at the list of the variables, and we get isobaric 3, that's the vertical coordinate. Again, thanks Grib for making things terrible. Temperature isobaric, the station name, station description, lat, lon, and time. Okay, great. So if we want to plot that up, I can pull those out of the Netcdf file just like you would do. Thanks to Jeff Whitaker, the Netcdf4 has this function that converts numbers to date. So the raw date that comes back are basically in hours since the start of the collection of grib files. For threads, that's about 14 days, depending which server you hit. So, that seeing plots of 300 some hours is not that useful. So num to date will convert that. It can read the unit string and parse that and turn those into Python date times. Great, we'll use that. And because matplotlib already supports date times, we can just throw those in the plot, and we get a nice 7-day forecast of temperature from the GFS for right here. So, what about using them together? MetPy plus Siphon. So the kind of complementary technologies, MetPy, while there are data readers, I've focused on things that are kind of special or things that are useful to me because, if I use Python to write NIDS code so I can test our implementation in Netcdf Java. But as far as getting data easily in, I think Netcdf is the best way because the Python API for it is just so lightweight to get into. The only downside was getting remote data, while OpenDAP gave you some capabilities there. NCSS is just an easy way to specify what you want in the way you're thinking about it. I want this lat long, I want this time, go. And so they kind of work together to get data into MetPy. So, for instance, we can look, let's plot a sounding from the GFS for Boulder 12 hours from now. All right? Or use the same NCSS query we had before, or the same NCSS access to hitting the GFS. But this time, I'm going to ask for the point, again, negative 10540. This time, I want one time, now plus 12 hours in the future. And I'm going to take that in CSV format instead of Netcdf just because I can. This time, I want isobaric temperature, relative humidity isobaric, U component, and V component. So all the things you want for a basic sounding, and then go and get the data. And then Siphon handles parsing that CSV into something you'd want to use. All right, here I'm going to take the data out of that CSV object and then attach some units to it so that I can easily convert things back and forth. So for instance, the vertical coordinates in pascals, I want that to be in millibars. Temperature by default comes in Kelvin. I want to calculate, I get relative humidity, I need dew point for the sounding, so here we'll use the dew point RH function, which takes temperature and relative humidity and gives you the dew point. Again, by having the units attached, it can make all the right sense of it. Here, take the data, it's being given to you in meters per second, and then we just call skew, and then I'm gonna, as I'm plotting, I want those in degrees Celsius, so I'll ask for it there, plot the barbs. This, I get too many pressure levels back from the server, so this kind of caps those off. I need to fix some things in MetPy, so for right now I'm just only plotting the wind barbs below 100, or lower than 100 millibars in height. Convert it to knots, and there you go. There's your forecast sounding for Boulder. So ideas for the future. Now, I've just been, generally speaking, we just open issues on the issue tracker on GitHub to track things that we want to do. That's just the easiest way to do it. Makes it easy to milestone them, and then people can see what we're thinking about. So for instance, things that are there right now are station plots with the weather symbols. Definitely not something you can do in Matplotlib easily today with the weather symbols is nigh impossible. Hodograph wouldn't be that hard, but it's not there in the sounding right now. And then also, I think being able to pull in data quickly from the sounding archive at Wyoming to be able to get historical soundings would be a nice thing. So for instance, here's an early prototype of the station plot. It's not ready for prime time yet, and I'm not remotely sold on this API, but this is some code I'd again scratched the niche a while ago, hacked it together, and it didn't really have a place to live. So I'm going to try and get that into MetPy with hopefully some changes into Matplotlib to facilitate this, but looks like a great station plot to me if we just had the weather symbols and maybe the visibility in the center. So right now what we need more use cases to drive development, because at least Sean and I being the active ones on it right now, boundary layer, radar guy, we're not your prototypical synoptic guys. I remember what we did in class, and I have certain things I like seeing, but I'm not trying to teach a class off this, so I'm not necessarily going to know the things that everyone else is going to want to see in here. What things do you need? Do you need ageostrophic winds, or is it more important just to be able to get a isentropic analysis, or is it just good enough to get a simple 500 millibar map with vorticity and maybe some of the station data from the soundings on there? I don't know. And so at least one of the things we want to get is more examples of highlighting. This would be a great example if I could just get X. We're just missing that one piece. So that's kind of what we're trying to get more of. So community participation is really the name of the game here. We can slowly keep accumulating things, but if it's just me and Sean, it's going to be a slow slog here as we keep piecemealing things. So the infrastructure is based around making this very maintainable. So for instance, we have automated tests on the service called Travis CI. So if we look at this, Travis CI is a continuous integration thing, and that's a big buzzword for software engineering. Basically, it means every time you check in changes to your code, things get tested, and you're always aware of how good your code is. Is it working? So for instance, here I made some README improvements. That's not really a code change, but every time I make commits, it runs a whole suite of tests. There are 5 sets here running on Python 2.7 to test code style, to test the unit test, to test the examples still work, to make sure that our minimum dependencies still work. And then we have tests on 3.2, 3.3, 3.4. So we really want to make sure this automatically gets done so it doesn't take any effort. I commit code and I get notified if I broke something. Or better yet, you make a pull request. GitHub runs this on your pull request, and then did you break anything in this pull request? And that's actually how we do our development, is make pull requests, put them up there, let Travis run and see, oh, I did this stupid thing, and fix it and keep going. We have code coverage automatically being run, so we know how much of the code is covered by tests. I think we're at 95% right now. Also have automated code quality, and then automatic documentation generation. And that's probably my other favorite here beyond Travis. So Read the Docs is a Python service that automatically builds your documentation for you if you set things up. So every time we make a commit, the documentation is rebuilt and uploaded here so that the users finding documentation always see the latest. In Python, if you're not familiar, there are doc strings. So the first line after a class or a function can be this string that documents your function. If you do things in a certain format, you can have tools automatically pull that doc string out and generate API documentation for you. So if you put a little effort into that, we see here we have, okay, here's our calculations. All right, let me go into the Thermodynamic API. Okay, here's potential temperature. Here's the name parameters, here's the returns, return type. Here's some notes. There's the formula for potential temperature, typeset with LaTeX. Here's an example using it. Not all of these are as well put together, but there are some good, good documentation of how to use this package. For some of these, here's a good one. Okay, here's the moist lapse rate. Here's the differential equation that gets solved to solve for the moist lapse rate. Here's a reference to the paper where I pulled out the equation. So if there's ever a question of how something works, where it came from, it's all in the documentation, automatically generated. So if you just put a little effort when you make your code, this happens for you and you don't have to think about it. In addition to the API documentation, the examples are done in Ipython Notebooks. So if you make a good notebook, we put it in here, and for instance, here's an advanced sounding one. Looks just like a notebook, and the plot's at the end. It's a little small, but here's this is sounding from May 3rd, 1999. So you can see here it was highlighting the positive and negative areas in the sounding. So the documentation, it's been very nice. It took a little bit to get that set up, but having that automatically generated so you don't have to think about it. And also, Read the Docs provides latest and stable. So you can also go back and look at the documentation for your most recent release in addition to what you've committed into GitHub. So basically, a lot of effort has been put into infrastructure here on this project. There's not as much features as I'd like. There's enough to get good soundings, but a lot of it is getting tests and documentation so it's easy to keep this going in a good way. It's tested. Things won't break as you add things and fix things. So getting and using MetPy. We've got 2.7 support as well as anything greater than 3.2. The packages are available on the Python package index, so you can just pip install MetPy and Siphon. Source is available on GitHub, and all the development really happens in the open in the issue tracker and pull requests on GitHub. And like I showed you, the documentation's online. So we really want to encourage contributions to try and make this as useful as possible to everyone. So if you've written something cool that you think people could benefit from, that doesn't even have to be specific to MetPy. You just have this cool Python function that you see isn't in here. Maybe theta E calculation. I know that one's lacking. Great. Open a pull request and start the code there, and we gladly help get it into shape, get the documentation, help get that there, write a few basic tests so it doesn't break in the future. Fantastic. Maybe you found it useful, but it's missing that one crucial piece. If you just open an issue and say, hey, I would love to use MetPy, I could replace my labs with this if I just had X, Y, and Z. Even opening an issue with that so we know what's missing is a great help. Better yet, you could open a pull request with at least a little bit of an implementation, but that's going the extra mile. Or if you've just, you've used MetPy in the future and you've done some really cool examples, we'd love to have them. Send them to us. Better yet, open a pull request with the example, just dump it in the examples directory and it'll get included in the documentation. So with that, I'm going to move on to the hands-on exercise, which is going to be just a running through a notebook here. If you go to the workshop page or it's on the Ramada server, the MetPy exercise notebook here. So like Stephen showed you how to download that in the last tutorial. You can run that in the Ipython notebook locally. So it's the MetPy exercise, IPy NB. Where did it go? So I'll start it up over here. Oop. I'm on the wrong branch. There we go. Start the notebook. There we go. Okay. And let's try and blow this up. That looks, I think, big enough. Okay, so there's a big block of imports at the start here, just trying to pull in date, time, things from Siphon, NumPy, the plots from MetPy, as well as the unit support and the calculation. Got some code up here to kind of on the instructions on the GitHub page, there were two sets of instructions for that environment. There was one that did the usual Conda thing. Unfortunately, MetPy and Siphon are not in any Conda repos, so you have a second step where you need to pip install MetPy Siphon. Yeah, we have a bin-star. I almost put it on Unidata's bin-star account, but then I didn't want to complicate the instructions with setting up a bin-star channel, so 6 of one, half a dozen of the other. I failed somebody. All right, so there's some code at the top here I don't want to get bogged down in to kind of help work around some issues. One thing here is handling the units, so we're going to be working with the CSV data, and so this little gem here will take the units from the CSV header and use that to assign proper units for MetPy use. And then there's another part here that handles the fact that getting point data from a thread server wasn't coming back sorted by time, so I kind of needed to make things work a little better here. So the first thing I want to do is just walk through getting a meteogram from some METAR data. So go back to threads here. If we go here, there's observation data on threads. Go in there, METAR station data. Excellent. And then here's our feature collection. We can go in here and get individual Netcdf files, but that's no fun. We'll just get the feature collection, and then we can query across multiple Netcdf files. So I'm going to come back to the notebook. Why are you not? Aha, okay. So make sure I run my code. Yeah, there's some harmless warnings there. All right, so got a catalog object by pointing at that URL. So now it's parsed that catalog, can make sense of everything. So I want to set up Netcdf Subset service access to that data set. So parsing this statement now is I get the catalog and it has a data sets, which is a dictionary of a name mapping to a data set object. I don't care about the name, I just want the values in that thing. So I grab the values, convert it to a list because that makes it Python 3 compatible, and then just grab the first one. So we need to improve the API a little bit to clean it up, but basically I want the only data set that catalog has. So I pass that into NCSS and I ask for the access URL corresponding to Netcdf subset. And then one little thing here I do is I install the MetPy unit handler here so that we don't have to work with the units after parsing the CSV data. It just does that transparently for you. And eventually that's going to be something handled in MetPy, but like I said, we're very early on here. So now that we've accessed the Netcdf subset service, first question would be, what variables does the METAR station data have? All right, great. We've got air pressure at sea level. There's air temperature. That'll be useful. Dew point temperature. What else? Wind from direction. Sure. And wind speed. I think that's good enough for me. So now we're going to create a query for the last 7 days of data. So I grab now, just datetime.utc now. So that gives the proper time for now in Zulu, so we don't have to worry about time zones and whatnot. I create a new query, so then NCSS has a quick function to grab a new query, and I go ahead and you can chain these queries together. And so I say, go ahead and we'll start off here and say accept CSV data, which is the way of saying I want you to give me back things in CSV format. Then the next thing we add on here is .lat point. So I'm going to request data for negative 97 longitude, 35.25, which is Norman, Oklahoma. Great, and then we'll go ahead and tack on here the time range. So starting point is now minus 7 days ago. So we're not looking at forecast data, we're looking at the METAR data, so I'm going to go back 7 days. Great, and then the other argument is now. So we're going 7 days ago to now is the time range on the query. And then we'll specify what variables we want. We want air temperature, dew point temperature, wind speed, and wind from direction. Okay, made the query. In the Ipython notebook, that already renders as the query string if for some reason you are wanting to be able to hard code that URL somewhere. If you're working in Python, I'm not sure why you'd want that, but for debugging, that was very helpful to have. So let's go ahead and get the data, and we'll call this post-process data function that just, like I said, handles the lack of time sorting. In an ideal world, that would not be needed, but the real world is far from ideal. All right, got the data back, already done. If we're curious here, we can go in here and say, what's in data? And we got air temperature in degrees C, dew point temperature, degrees C, latitude, longitude, and a whole bunch of the station. All right, anyhow. So the first thing I wanted to do here was let's calculate heat index. Try and use some of those calculation functions that MetPy has. So first we need relative humidity, which is your water vapor pressure, partial pressure, divided by the saturation vapor partial pressure. Fortunately, MetPy provides calculations for those various things. So your ambient vapor pressure is just a saturation when you pass it to the dew point. If you're not sure about that, that is in the documentation for MetPy. So, okay, mcalc.saturation vapor pressure. Pass it in data, dew point temperature. That gives me E. E sub S, the saturation, same thing. We'll just pass in the air temperature. And then relative humidity is just dividing those two. If you want to see, whoop, don't do that. All right, there we go. Relative humidity, 0.8, 1, 0.94, so we're not getting anything crazy. Good, and comes out dimensionless, also good. So now we need to calculate heat index. So we can call the heat index function with the data, the air temperature, and then the relative humidity. With the one warp that I noticed as I was putting this together, for some reason, when I coded up heat index, I decided I should take heat index in 0 to 100, as opposed to being consistent with everywhere else. But still works. So multiply by 100, calculate heat index, bang. So now I'm going to make a poor man's meteogram here. If you're not familiar with matplotlib on the plotting, has a lot of power to make multiple panel plots and everything. So we're going to plot air temperature and dew point and our heat index on one panel. Then we're going to plot wind speed and wind direction on the other. And I do a little magic here to kind of make a second y-axis for the wind direction on the same plot as wind. I don't want to get bogged down in matplotlib details. If you're curious, I'd be happy to talk afterwards. But the important part is here's plotting the data from MetPy. And here's your top one. So there's your dew point, your temperature, and then the heat index. So you notice the heat index function is smart enough to not produces a masked array. And the values are masked when heat index is a not valid calculation, when the temperature or humidity is too low. Percent matplotlib space inline. And I think I have that set default in my settings somewhere. You notice there's no heat index here when the temperature's low, and then you get a nice spike here when the temperature's hitting 90 Fahrenheit and the heat index is up around 95. So looks pretty good. And here you get the wind trace. The wind direction here in the black crosses and the wind speed in the blue. All right, and then, to get the nice, by using date time objects, Matplotlib handles turning those into strings for you. So you don't have to care out of the box about the time parsing. All right. So then the other example here is plotting a sounding. So I was going to look at, using the GSD, NOAA's local run here of the HER. Slightly different from the NSEP version. The most important thing to me was I get more pressure levels with this one. So that's why I'm using the GSD one. So if I go to the catalog, we got a forecast model data. And there's the HER GSD. So I want the GSD in WRF pressure levels. Great, there's the best URL, great. So I already put that there for you, so we'll run that catalog. Same thing as before, I just want the only data set in there. We'll set up NCSS access, just like before. So now, what variables do we have on the HER? All right, not too many from GSD, which is good. I don't need a lot. We have dew point temperature. Great. There's temperature. Awesome. And U and V component of wind. Everything I want for a sounding. All right. Same thing again. Set up the query to get CSV data. I'm going to just do it for Boulder again. And now we're just going to pass it UTC now to get the latest in its sounding, or in its data. So quasi-current. And then we're going to ask for temperature isobaric, dew point temperature isobaric, UV, etc. So do that. Get the data. Sometimes takes a little longer to get it from threads. There we go. All right, data's been. I'm going to go ahead and pull these out as T, TD, and P, because for one, makes it easier to call it P than remembering its data vert coord. Because it's actually a coordinate axis of the model data. It's not, an observation field. All right, fantastic. And we can just throw this into the SKUT function. Create a SKUT, plot pressure and temperature, pressure and dew point. I'm going to, because the HER goes up to, I think it's like 50 millibars or something, I'm just going to cap it from 1050 to 100 millibars. Actually, I think it goes higher than 50, but anyhow, set the Y limits and we'll plot our special lines. All right, there's a good start. Got a nice little nose there. All right, let's go a little further here. I'm going to calculate the parcel profile. Now, one of the things I learned here is the WRF pressure values come out increasing in value, but that's decreasing in height, which apparently the way I was calculating parcel profile didn't quite like. So what I do here is I just pass in the pressure flipped, : -1. If you're not familiar with NumPy slicing notation, essentially that means give them to me in reverse order. And then I also take the last temperature and the last dew point values. Those are the surface values. All right, so I get that parcel profile, and then I throw that into a plotting function on the SKUT. All right, that looks nice. It looks sensible for the parcel profiles you'd expect. We'll go one more step here. I'll go ahead and calculate the LCL. The parcel profile did that for me, but I want to have a nice dot to denote the LCL. So I can calculate the LCL here. Again, the starting point values are the last in the array, so we pass it last pressure, last temperature, last dew point. And I'll go ahead and calculate the LCL temperature so I can plot it properly using the dry lapse command. Plot that on there, and I'm going to go ahead and I want to plot a nice straight line across the zero isotherm. Since the temperature is your x-axis, you can use the Matplotlib's AXV line, or an axis vertical line. So it's a vertical line that stretches the entire direction of the other axis. So that gives me a full range along the temperature, constant temperature line, or the 0 isotherm. So 0, I'm going to make it blue, dashed, and thick. And there we go. So nice 0 isotherm if you care about where the freezing level is on your sounding maybe. There's the denoting the LCL and the parcel profile. So just some fairly routine sounding analysis using MetPy. So with that, I think I have time for some questions.